Okay. Mr. Bu. So these are 5 types of transformers, guys, used in the industry. The first one, I know it's busy. I'm sorry. If you look at the blue. The blue is the first one. There's one. This is single phase transformer, 7200 volt on the primary. On the secondary side is 240, 120, 2 hats. Very commonly used single phase residential, plus light commercial up to 800 amps. Don't hold me on the amps, please, but these are kind of plus or minus. Where would I use this service? These are 5 different services that you can get from utilities. Service number 1 can get you a 7200 volt on the primary. You have no control over it. On the secondary side, get you a transformer, 2 windings or center tap transformer, 2 hats, neutral, single phase. You guys are very familiar with this. This is what we did in the residential, 120, 240 single phase. It's mostly residential plus light commercial, you'll see it, and mostly up to 800 amps, though it can go higher than that. Mostly up to 800 amps. Any question? This is one type of transformer. 1 coil, 1 phase. So we did mostly, guys, light commercial, residential, mostly. You move to industrial, commercial, you move it to 3 phase. Okay, any question, guys, about transformer number 1 or service number 1? And these are called low voltage services. Anybody knows what low voltage service is? Because all the voltages on the secondary side, not the primary, are less than 600 volt. These are not, there's low voltage services. Okay, look at the second one, guys. Second one is a delta. I have a delta center tab. Delta. On the primary side, Brad, 13.8. This is a 13.8, 13,800 volt. Utility type, I have no control over it. On the secondary side, that's my baby. I have 240, 120, except it's a 3-phase. That's the only time you can get 3-phase 240, 120 is from this type of transformer. That's that bad boy center tap transformer. Your book, guys, is talking about it, and my quotes. I will remind you of center tap transformers. They have a leg that's called the wild leg, the bastard leg. This one here, that's called the wild leg, the bastard leg, and this one has to be identified as orange. And most of the time, unlike I did it here, most of the time, this will be a phase B. So it's a phase B, and it's wild leg. You're not supposed to use it. If you read through the book, it's not supposed to use it as line to neutral. Okay, so advantage of this transformer, guys, center tap transformer, is where do you use it? Commercial plus light industrial. You can go all the way up to 1600 amps. You can go higher than that. Typically 1600 amps, 3-phase. Remember, 3-phase. And it powers, Mr. Irbab, if I want to add something to this, I would say if you have a load 10% or less single phase, this would be an ideal application for you. If you have Muhammad, my friend, if you have a situation where 10% or less of your load in your building, or less, 10% or less, these my rule, 10% or less a single phase load, meaning receptacles and lights. This is a good application where you can use a delta center tap, delta center tap. I've seen them. I told you guys, I don't know if I told you about this one. I've seen them in well houses. You have a room like this for the city of Minneapolis or city of Richfield, all these cities, and full of these, they dig a well and they pump the water for the city. And you I don't know if you've ever been in the well house. It's full of basically pumps, pumping water into the city water system. And almost 90% plus of the load is 3-phase, 240 motors. And only 10% is 120. What that's 10%, guys? There's a couple of receptacles on the wall, convenient, and a couple of lights. That's all what you need in the room, so people can walk in and plug in something and do maintenance. So that's a good application for it. You would never use this, Brad, on a commercial building, this service. It's not a commercial building service. It's not an industrial building service. This is specifically rated for when only the load is very small, the low voltage. The line to neutral load is 10% or less. Yes, sir.
So delta is really dependent on applications being used.
Absolutely. These are, all the 3-phase I'm going to be talking guys about are application dependent. Delta, especially the delta center tab, guys. The delta center tab, it's called center tab because they see how they ground the neutral right in here. I don't know if you can see that one. This goes to Mother Earth. They're grounding it. This is light commercial. Light commercial. Um, I mean, commercial plus light industrial. Commercial plus light industrial. If you want to write next to it examples, well houses, I've seen them a lot in well houses. A lot. That's where I've seen them a lot, personally. And everybody knows what a well house is, you know, pumping water in the cities, or wastewater treatment, not lift station. Anybody have seen lift station? Where they take the stuff and lift it? Lift station, a house, you have a house that has all the pumps, all the pumps that lift all the sludge stuff and pump it into the wastewater treatment plants. All the motors are 243 phase, except a couple of lights and a couple of receptacles convenient in the wall. That will be a great application for it. A great application for it. Okay, and look at the voltage that they use on it. The only voltage that I'm aware of, Brad, that they use in this system is 24120. I've never seen any other voltage that's used in this particular system. Is 24120. That's it. It's 3-phase. Okay, any question guys about 1 or 2? These are 2 services, 2 transformers. If you go to 3, now moving on to guys 3, if you look at 3 here, I have 3 and I have 4. Let me move this one away. There you go. I have 3 and I have 4 and I have 5. These are commercial, mainly commercial industrial services. That's what you're going to be looking at. A commercial building, that's exactly what you're going to be looking at. The only difference between these 3, 4, and 5 guys are the voltages, the voltage level. Okay, so you can specify, this is what you, Brad, you're going to be specifying services. When you ask Excel for a service to your building, you're going to be picking one of these 3, 4, or 5. Let's look at 3. 3 is on the primary side, 13.8. I care less on the primary. Most of the time, guys, I put the 13.8 for you because that's what we'll mostly get in the cities here, especially in the cities. Mostly you get 13.8 on the primary. I have no control over it. On the secondary side, that's my baby. I get 208, 120 on the secondary side, 3-phase system. Where would I pick a system like this? If you have residential high-risers, apartment building, that's a good system to pick for it, 3-phase. Commercial plus light industrial. Commercial plus light industrial, that's a good application for 208, 120, like the project that we guys have. So that's, again, suggestion. Talking to Hallberg, here's what the Hallberg told me, and a few people do use that. If you have a building 15,000, close to 15,000 square foot, or larger than 15,000 square foot, larger than 15,000, well, since we're here, let's say 15,000 or less. If you have a building, 15,000 square foot, let's say square foot here, and let's delete it from right in here. If you have a building, 15 square feet is 15,000 or less, a good application for commercial building, a good application is this service, a good application, commercial building. Higher than 15,000, you might have to jump into the 482.77. Suggestion, rule of thumb. I hope you understand, these are not code. You can use any service for anything almost. Okay, residential, high-risers, commercial. Here's a commercial square foot, less than 15 or less, rule of thumb. If you go light industrial, not heavy industrial, light industrial, not a whole lot of machines in it, that 208, 120 is a good application. Any questions guys about number 3? 3-phase service, perfect for non-residential. The last one is 4. 4 guys is, this is the most common for heavy commercial and industrial. 482.77 system on the primary side is still 13.8. 482.77. Heavy commercial industrial, big buildings. When I say heavy commercial here, I mean square foot of larger than 15K. Again, rule of thumb. I hope you guys, you go down talk to the guys that you work there and say Chad said this, they might say, who the heck, where did he get that number from? I hope you understand. Rule of thumb, how I see it. There's nothing says that you don't have a 10,000 square foot commercial building and you don't and you bring a 480 to it. There's nothing. The idea, guys, if you have 15 larger than 15, the building is large enough to justify the price of a 480 switch gear. That's the whole idea. Because you go to higher voltage, the equipment gets more expensive. More efficient, but more expensive. The chiller that you're going to run at 480 is more expensive than 208. All the equipments that you run at higher voltage, efficient though, they're very efficient, but they get a little bit more expensive. Any question guys about 48277? Very commonly used for heavy commercial and industrial. I've never seen number 5. I've never seen or wired the system, personally, but I read and heard the very large industrial plants guys and the Canadians, they use a 600/347. 600 volt line to line. You go 600. I've never wired it. I've never seen it wired. Anybody ever worked in 600? Canadians do it, but you could not commonly used, at least my experience with it. Somebody else somewhere in the country probably using it. But since the voltage is higher, really very large industrial plants use these voltages. You would never put this voltage 5 on a commercial building. It doesn't justify it. At least from my experience. Disclaimer. So you basically, if I am to summarize this, in our project, you are really here or here. Most of the time, you're here or here, between these two voltages. Most of the time, 90% of the time, Brad, you're going to be between these two voltages. Really, in commercial industrial, 90% of the time. Any question, guys? Any question? We call this is low voltage services. Again, the book, chapter 12, guys, talk about the induction and eddy current and all this basic stuff. Please read it on your own. I grabbed the application of the transformer, not the theory of operation and induction, all the stuff. So we don't want to. I don't want to spend. I know you can read it. I know Gary covered it. I'm going to cover the things that you're going to use directly for transformers. Okay, this slide is going to be PDF. Any questions about that? So that's these are the most common services and transformer that you're going to be using. Now, I want to bring to your attention, guys, one little thing. Here it says low voltage. Can you next to low voltage? This is means. What does a low voltage mean? Equal or less than 600 volts. That's in the power language. Low voltage is in the power language is equal or less than 600 volts. Look at all these services are on the secondary side. On the secondary side, they're equal or less to 600 volts. On the secondary side. The primary side, I care less. Could be any voltages. Most of the time, the primary is going to be 13.8, 72 if it's single phase. There's another voltage, guys, 4,160 volt, used in certain communities. But I'm caring about the secondary side, because that's where I have my control over my transformer, right in here. Okay, I bring to your attention to low voltage service, less than 600 volt. If I'm going to go to the next slide, guys, this is a high voltage service. What is a high voltage service? More than 600 volt. Can I use a high voltage service more than 600 volt? Yes, no problem. UVM is using it. If you work with UVM, 3M is using it. Mayo Clinic is using it. These are the type of building, guys, that they can use a high voltage primary service. They call it primary service. Higher than 600 on the secondary side. On the secondary side, okay? Look at what they're doing here on the secondary side. Most of the time, it comes delta delta. Most of the time, look at the primary. Like if you go to UVM, they have substation high voltage. On the secondary, on the primary side, look at the voltage that they're bringing to the transformer. 69 kVA. That's a high voltage. Or 115 kVA. kV. These are your primary. Look at your secondary side. You can bring commonly used 2400 kVA, guys, very commonly used, or 4.16, they call it 4160, the common term for it, 4160 volt or 4.16 kVA, 13.2 or 13.8. This is, when I was doing medium voltage, was our voltage of choice. Our voltage of choice on medium voltage. Our voltage of choice. So if my plant, and a lot of people guys are using it right now, if my plant, because of future expansion, if my plant need a primary service higher than 600 volt, take 13.8. 13.8 is the best, more efficient, higher voltage primary service. Though you can get any one of these voltages. Most of the time, they give it to you guys delta delta. Most of the time. Why? Anybody knows why delta delta? Because on the primary side, if you get that high voltage, do you really need one line to neutral? We don't. On high voltage, other than utilities, you don't connect anything line to neutral. there's no need for line to neutral. Because remember, if you are at the U of M and you have multiple buildings everywhere, what they do, guys, is they have a substation, medium voltage substation, 13.8. So this transformer land into a big fat switchgear medium voltage, 13.8. They have a feeder that goes to building A, that goes 2 miles away from here. Another feeder that goes to building B, that goes 3 miles away from here. And you keep going all these medium voltage underground. They have tunnels underground, and they push all these 13.8 feeders to go to different buildings. When they reach building A, guys, the substation, here's your 13.8 feeder coming to the building. The high voltage section is here. They have a transformer to transfer it down into 480, because you can't put 13.8 across that light or across a chiller. You cannot. So you transfer it down into 480-277, and from this side, now you get your 480-277. You feed all your mechanical equipment, lighting, and receptacles to another transformer. Then take it 120. So any question, guys, about this? I thought to throw this one on, at you, because you're going to be encountering good customer for this. If you want to put, guys, I've seen them anyway. 3M has this. U of M here. Mayo. How do you spell Mayo? M-A-Y. Oh, Mayo. Oh, it's easy, Chad. Mayo. There's another O?
No.
Mayo.
So you have to have a center point on that, if you're gonna go like into the building to have the neutrals. Do you have to have a center point right off the transformer? Or can you...
When you have medium voltage service, you create your own neutral at the low voltage level. Yeah. When we have a medium voltage service like this, I show delta, guys, because you really don't need a medium voltage neutral. Is meaningless in the buildings. For utilities, they use it all the time. For us, you're not going to tie, by the way, the medium voltage for 13.8, divide this by square root of 2, I think it's 7200. This will give you 7200 volt. 13.8 divided by square root of 3, square root of 3, 7200. You don't tie anything 7200. You know, you take this transformer, move it 4 miles to a different building, the cable, and then you have a substation where you transfer it back again to 480-277 most of the time, or 28120. So you take these feeders, guys, and you transfer it down into one of these three services. Here's where 13.8 coming in here, and then these you dump this power voltage into your building as one of these, the last 3 forms, 3, 4, or 5.
So how do they generate the neutral? Do they just go off the ground then?
Yeah, you create your own neutral. See what I did here?
Here's
Here's my feeder coming in here. You tie, if your service is any one of these are Y, delta Y, meaning neutral. You tie this to Mother Earth. You establish your neutral, and you pull.
Oh, so it could go delta, and then you can pull a Y in on.
Absolutely, no problem. Yes.
Okay.
It could be, so it's a delta, where were we here? It's a delta here,
Yeah.
and then on this, when
You
we
have a
move,
delta Y on the.
yeah, let's say move another, let's move another mile, there's another delta, so these are coming here to another transformer, and from this transformer, I have a Y. Okay, that's how they take the service and distribute the service in the building. Make sense? They take that delta to another delta. These are two different transformers. I hope you understand. This is one transformer. This is another, and the distance between them is a couple of miles. Could be, you know. That's why they choose this high voltage. That's why you choose this high voltage. Any questions about this? Any question about this? So that's basically what I wanted to at least touch about the transformer use and so forth before we okay, then the coming, guys, is I'm going to go and size. Any question about the services? That's it. Primary service. This is called primary service or high voltage service. The other one is low voltage service. Most of the time, guys, 90% of your time probably will be working on low voltage service. Okay, so here's now this is just info. Here's what I'm going to do, guys. I want you to do, we're going to do some calculation, transformer calculation. So we're going to go to Article 450. here's what I'm going to, really, just to give you a heads up. I'm going to take a couple of transformers. I'm going to size the primary fuse and feeder, the secondary fuse and feeder, primary fuse and feeder, secondary fuse and feeder. That's what we're going to be doing. Primary fuse and feeder, secondary fuse and feeder. So that's basically what we're going to be doing for this transformer. And then then we're going to do bonding and grounding for a transformer. So to help me with this, go to 450, will you? 450 talks about how to do all this business. 450, 450, 450. There you go. In particular, I want you guys to go to 450 table, 450.3a and 450.3b. Table 450.3a and 450.3b. We're going to be using these two tables, guys. Everybody's there? 450, 450.3a and 450.3b. 450.3a and 450.3b. Are you guys there? Let me ask one more time. Are you guys there? Okay, let me ask one more time. Am I there?
No.
And you see? Okay. There you go. Look how many clicks. I should probably move it away to a better location. Okay. Let me just open 2000. You guys have 2008, not a big deal. They're the same. What did we say? 450? Let me just go. 450. Here's my 450. Just to highlight a few things here. Article 450. I'm looking at 2011, guys, the same way. Okay, here's a table that I want you guys to use. Make sure that you know how to use it. 450. Number one, I want you guys to look at this table. You're looking at maximum rating or setting of overcurrent protection device for transformers. Over 600 volt. Over 600 volt. Did you guys hear that one? Over 600 volt. Meaning the primary. So over 600 volt, meaning the primary or the secondary are over 600 volt. So here's the primary. I can't emphasize this one. This table, you use it if the primary or the secondary are over 600 volt. Okay? Or both. Or both. All right. Any location. Here's where you're going to be unless you hear otherwise. You're always going to be in any location. You default as impedance of 6%. Always. Unless you know otherwise, okay? And primary protection over 600. If your voltage is over 600, like 13, here's an example, 13.8 kV. That's a good example, over 600. Primary, unless you know otherwise, Brad, you're always fusing. Always fusing. You're always fusing, unless they tell you otherwise. On the primary side. On the secondary side, this is the primary side. On the secondary side, you have options. Option number one, is your voltage on the secondary side higher than 600 volt? If so, you're going to be using over 600, most likely going to be using fuses, and here's what you do. If your voltage on the secondary side is lower, remember, lower than 600 or less, then you only have one option, fuse or circuit breaker. Does that make sense? I can't emphasize, guys. And here's your transformer. Here's my transformer here. Here's my 13.8 here volt. Here's my I'm going to use 480. Okay. If this is, I'm showing just one winding. If this is my transformer, where do you think I'm going to be? I'm going to be using the fuse for the primary, because is the primary higher than 600? Yes. And is the secondary lower than 600? 600 less? I'm going to be using 120. Any question? I want to bring to your attention note number one right here. I want you guys to read it. But if you read it, DJ, you read on your own. But here's what I'm going to summarize it to you. It tells you if you did all this calculation and you end up with a non-standard fuse or circuit breaker, what do? Go up. So I can't emphasize, wherever there is a note number one means go up. What if you don't have note number one? Bill, you have two options, three options. You go sit in the bar, drink and cry, custom design yourself a fuse that's 13.33 amp, or, for example, or go down. which we normally go down. Any question, guys, about how to use this place? Supervised location only. This is you use the application for supervised location, guys, if you are like the UVM application where all your equipment, you have your own electricians. They're maintaining the 24, well, not 24, you have your own staff of electrician. They are maintaining all your system. You use supervised locations. But if you are a Dunwoody building, we don't have our own crew of electricians. You don't apply this rule. Any other building that don't have their own crews of electricians to maintain it, you don't apply the supervised location. So most of the time, you're going to be with any location exactly what I told you, unless you know otherwise.
Would an electrical shop servicing this building be? Or do you have to actually have employees that are working for like the U of M or something?
Supervise if you farm out and you have everything is under locked keys and maintained and all this stuff, that the way I interpret it, it will be supervised location. You don't have to have them hired, but you have them locked down. People who have all these keys of all these equipment are Werner Electric or like Hunt Electric or so. Supervised installation. Any question, guys, about this? Everybody knows what the percentage is. This is percentage of full load current, the full load current. Okay, so this is, when do we use this one, guys? We use this one only if the primary or the secondary or both higher than 600 volt. Listen to me carefully. Primary or secondary or both higher than 600 volt. Or not and, because look here, the secondary could be lower than 600 low, but the primary is still higher. Any question, guys, about using this table? Okay, so that's table number 1 that we need to understand. Click on that one. I want to go right underneath it, my friends, which is table number 2, which is B. B is very easy. You guys look at B. This is only for voltages 600 volt or less. 600 volt or less. That's what we most of the time are going to be. Here's my transformer. I have a 480 from this side. From this side, I have 208. So Spencer, my friend, both voltages are what? 600 or less, right? All right. Here's where your default is. You're always defaulted to. This is kind of the interesting one. Primary and secondary protection is your default. Primary and secondary protection. If you're doing primary current less than, most of the time, you're going to be current of 9 amps or more. So that's basically most of the time you're going to be right under here. Current. These are just for tiny little transformers, guys. Current less. Look at that. Current less than 2 amps. Current less than 9 amps. This is a very small transformer. Controlled transformer like these ones on the wall. So that's where you're going to be. On the primary side, it doesn't say a fuse or circuit breaker. You can do it for either. On the secondary side, my friend, current of 9, you're going to be always almost here, and you're almost going to be in this application, 125%.
Okay, where's that where you don't have to have the secondary protection on it?
Cool. That's your tab rules. The tab rules.
Oh, the tap rules?
Okay. I promise you guys, when you have, where would I use primary only protection? Tabs. A good example of this, 25, you have a 480-277 panel here. You grab a 480-277 feeder to a transformer sitting here. From the transformer, 480 on this side, 208 on the other side, take the 208 to another panel. All of them are within 25 feet of each other. Then you don't have to have a secondary protection right next to the transformer. Your secondary protection can be right inside the panel. They use it, guys, all the time. I promise you we'll do this, the whole exercise when we do in the industrial more. Let's just do primary secondary now. But that's a very good application where you can have primary only protection. So your primary will be right here for the transformer, primary, and for the secondary conductors. But your secondary conductors will be landing on a main for the panel. Main for the panel. Okay, any questions, guys, about this table? Everybody knows how to use this table. I want to bring your attention again, Mr. Erbab. And you can annoy me if you want to. Note number 1. Note number 1, what does it say? If you read it, it says if you don't land on a standard, go to the next one. So these are the most important things in these tables. Any questions, guys, about these tables? before we take an example of how to use them? Everybody knows how to use these tables? Very important. So that's, let me take an example then, if you guys don't mind, because you're my friends. Any question about this? Any question? Mr. Bew, did I put you to sleep, my friend?
No.
My sincere apology if I did. Okay. There you go. This is the nice thing, it captures it too. Isn't that cool? Can you guys say cool?
Cool.
Okay, thanks. Don't go tell your husband that our teacher lost it. Okay, so I can't emphasize, guys, here's what we did, and these are also captured as a PDF for your reference. I hope you guys appreciate that one. This is, it really, I think it's nice. I'm so excited about it. I don't know about you guys. All right. You guys want a five minutes break to go to the bathroom and come back? Because I need to continue with a whole lot of stuff. Is that a good break here before I start it?
Yeah.
It's still there, if you don't mind. Because otherwise I'm gonna go 1/3 and then give you a break and interrupt my brain of thoughts, and then I used for receptacles. Typical transformer used for receptacles. Okay, delta Y for 8208 120. We need to size the fuses and the circuit breakers both on the primary and the secondary and the feeder. The primary and the secondary and the feeder. Okay? The primary and the secondary and the feeder. All right. So I'm going to go. Any question guys about here's a transformer, typical transformer. Okay. I'm going to start by number, which one is number one? Number one, guys, is the primary feeder. Primary feeder. To find the primary feeder, guys, I need to find I primary. You guys remember how we find I primary? You take the kVA of the system divided by 1.73 times what voltage on the primary side? 480. So you need to find the current, and that will get you a healthy 120 amp. A healthy 120 amp. A healthy 120 amp. Okay? Now here's the moment of truth. The moment of truth, guys. My Colts use 1.25 to size a conductor based on continuous load. Other people don't. So let's just use 1.25. But you don't have to use 1.25. When we go to the commercial, I start telling you guys. We start by sizing. Here's how I do it. We start with the load here. We size the load. If it's continuous, we multiply by 1.25. Then we size the transformer. Now the transformer accommodate the 1.25. Then we size the conductor. So we don't have to multiply by 1.25. In this case, huh?
I'm just,
Oh, okay.
that's how they do it in the D-wall.
D-wall.
By 170.
Yes, I know that. And my coach is doing the same thing. I'm going to do it this way. But I would do it, guys, and when we do the building, is I start with the load, take all the continuous, multiply by 1.25, so you increase the load, then you size your transformer. Now the transformer is accommodating that 1.25, then you size the conductor 100%. So I want to use 1.25 though, just to stay consistent. And why it's continuous load? Really, there's nothing, if you go read through the code, nothing tells you they have to multiply by 1.25, nothing. So you take 1.25, multiply it by 1, 2, and if you guys go there, that will get you 150 amp. If you take this one to 310.16 under which column? 75-degree column. What do you get? How many conductors on the primary side? 3 conductors, 1 aught. What insulation? Most likely THHF. 1 off. Any question, guys? Straightforward, no gimmicks, nothing. No gimmicks, nothing. So let's go to any question about sizing that. So we size the conductor on the primary side. We size the conductor on the primary side. I need for the same thing, a primary. By the way, everybody knows that this is the primary, this is the secondary, right? Terminology for transformer, that's, I assume everybody knows that. Primary over current protection device. Primary over current protection device, you take the 120, you need to go to table, now both of them are less than 600, so which table am I going to go to? 450.3 A or B? B. If you guys go to 450.3b, what's my multiplier on the primary side? 120 times 250, 2.5. 2.5. Are you guys there? The 2.5 is on the primary side. Remember, we're going to B. Okay? To B, because both of them are less than 600.
No, I understand why we're using table B. I'm wondering why we're not using the 150 amp instead of the 120.
The 150 is because it's multiplied by 1.25. That's just the size of the cable. You always start with the actual amp, the transformer amp. The 150 is the cable amp. Okay, so if you guys came up with this, I came up with 300 amp. Anybody came up with something different?
Sure.
If it's not, hey bud, need help or?
Yeah, I need to see.
Okay, later on.
What time do you think?
10:30. Yeah, no problem. Okay, so you take this one to 240.6, and you're gonna find that, by the way, a 300 amp is a size of a fuse. If it wasn't the size of a fuse, Holly, what do? Why? Because it doesn't tell you to go up. You can't believe over the years how many students say, Chad, why did you? It doesn't say go down. You can go sit in the bar, drink, and cry. You can custom design yourself a fuse, or you can go down. 300. I'm just waiting for somebody to say, Chad, how on earth would you put a 300 amp fuse on a 1 off? If it's bothering anyone, bothered me for years. Why would you do that? Because of the tab rules. This transformer, most likely, guys, this fuse will be within 25 feet of the transformer. If you put that fuse or the circuit breaker further than 25 feet, you have two options. You have to up your conductors. You have to up your conductors to a higher level to accommodate for the 300 amps. So there's a rules of tab rules. We're not going to get to the tab rules, but you're good. Make sure that your fuses are not further than 25 feet away from the transformer, which is most of the time, guys. You bring the panel here, the transformer here, and the second panel here. So really not big of a deal. Any question, guys, about the primary and the secondary? The primary overcome protection device?
We're always using primary and secondary to size that instead of using the from 453B instead of using the top one for primary.
Primary only. If you want to use the primary, the reason why I will always say, guys, you always use primary and secondary, because most of the time we use a transformer like this to get us what? To get us a 208 120, and that we dump it into where? Into a panel. And guess what's going to be inside the panel, right at the top of the panel? A circuit breaker. So most of the time, really, you're going to have primary, secondary protection. Most of the time. Now, if you have a machine, though, here's where you can. Say you have a machine, and the machine is running at 208, I'm just assuming, and the voltage here is 480. You bring a feeder to the machine. Here's your transformer next to the machine, and from the secondary, you dump the voltage right through the machine. No panel, nothing. then this is a good application for a primary only application. Because you don't have a distribution system. You don't have to just directly going on the 208 side and feeding the machine. One load. Any question guys for this transformer? Now on this side, now I can go land 150 amp panel here. 150 amp panel on the secondary side. I'm not going to talk about the panels guys because when we land panel on the secondary transformer, there's a few tweaking that I like to do. But you can think of it that this 3-aught can land on 150 amp panel now, feeding it. Okay, before I leave this, I will bring your attention, my friends, into grounding here. And so if I want to go bond, I want to use bonding and grounding. So here's this block here is my ground. This is my neutral. I'm bonding the ground to the neutral. And I'm gonna use a cable here that says where are we? Number 5. And I want to go grab that bonding jumper number 5, number 6. I want to size these two for the transformer. I create a separately derived system. That's what we call a separately derived system. Separately derived system, right? Right at the transformer. There's a cover bar that's for ground and a cover bar for the neutral. You tie the two together, and from the cover bar for the ground, you go to Mother Earth, or you can go to the steel of the building. We'll get into 5 and 6. Let's do 1 and 3 and 4. Any question about 1 and 2, Mr. Rabab? Yes, sir.
Can you explain to me why that's a separately derived system?
Oh, why? Because I created a neutral. Do you have any neutral on this side? You created a new neutral. Every time you create a new neutral, it's a separately derived system. Every time you create a new, meaning you go delta Y. If you go YY, which we rarely do, and you tie the neutral of the primary with the neutral of the secondary, it becomes non-separately derived system. It's a separately derived system because you created neutral. Show me where the neutral here. Do you see any neutral here? Do you see any neutral? Where's the neutral here? Right? There's no neutral. I created a new neutral. That's a separately derived system. We'll get into that one, guys, deeper when we go to transformers and generators especially. But for transformers, always ask yourself, Greg, if you created a new neutral, it's a separately derived system. If it was a delta-delta, not separately derived system. If it's a YY and tie the two neutrals together, which we rarely, if ever, use it, non-separately derived system. 99% of the time, you're going to see a transformer delta, Y, create a new neutral. This neutral will be the neutral for the 28120, and there might be another neutral there for the 480, 277. There might be in the building, which almost always there will be two neutrals. One for the 277 and one for the 120, and we do not tie these two together, the two neutrals together. We keep them separated. That's why separated derived system. You created your own new neutral. And I created as many neutrals as I go, as long as I go delta Y. You can keep creating as many neutrals as you want. And bond neutral to ground again. Neutral to ground. Every time you create neutral, you have to bond. Okay, let's go do number 3. Number 3, my friends. DJ, what was number 3? What? Number 3 is secondary feeder, right? Feeder. For the secondary, right? Secondary feeder, I need to find I secondary. And if you don't know how to find I secondary, Holly, I'm going to send you directly to Mr. Ryman across the hallway from here. Right? You can handle him. So everybody knows how to find a secondary of a transformer. I hope so. That's not where the class is here, because you've done it with me before, and we've done with the Ryman. So it's 100K divided by which voltage? 1.73 times which voltage? 208. Thank you, because we're on the 208 side. 208. And if you do this business, did I do that one? I did it here. I came up with 278. 278 amps. Okay? Piece of cake, Chad. Then I need to, again, questionable. DeWalt and Mike is doing 1.25 safety, no problem. But you're gonna find later on you don't need to do that code-wise. Okay, but we're gonna do it 1.25 for the test anyway, times 278. Why? Because we're assuming it's continuous load. And if you do that, you'll end up with 348 amps. 348 amps. Okay. Now 348 amps. Take this one to table 310.16 under which column and why? Why? Thank you. 75 column over 100. And let's carry this with one feeder, will you? That will give me how many conductors? Full neutral. I'm going to carry full neutral. How many conductors and what size? 500 kcm, 4 of them. So 4 conductors, 500 kc and m. Now here's where you can monkey around and start, guys, if you know your load, you can start derating the neutral. But in this case, we're carrying full neutral. See where this becomes happy? Because how do you derate the neutral in a transformer? I tell you how you derate it. You need to know what load is the transformer feeding. That's why I start with the load. I always start with the load. And you guys are going to be later on when you start with the load. How do you size even? How do we come up with 100K? Why not 200, Chad? Why not 300? You guys are going to be coming with 100. How would you come up that I need 100K transformer, KVA transformer? Start with the load. Always start with the load. You take your load, multiply the continuous by 1.25, keep adding them up, you come up with 100 kVA. Now that 100 kVA includes the continuous. Then, if you do it this way, guys, then you don't have to multiply again by 1.25 because it's already incorporated in the transformer. That's how you do it. And in the code, it doesn't tell you that either way in the transformer, the cable does not tell you. It's a judgment issue. Judgment. But because we size the transformer, I incorporate my 1.25 in the size of a transformer. I already oversize my transformer. So, and it makes more sense, guys, when you tie it to a panel. It makes a lot of sense when you tie it to a panel. If you do it this way, you end up with a transformer that can give you 120 amp and a panel that's 150. So the transformer can only give you, no matter what you do, it cannot give you more than 120 amps, but your panel is rated for 150. So, and the cable is rated for 150. So that 30 amps is worthless because the transformer will never be able to give you the extra 30 amps. Anyway, any question about this? Mr. Erbab, my friend, the next one is going to be number 4. What do you guys think? Secondary overcurrent protection device. Okay, if you guys go to table, the same thing, table 450.3 and B, on the secondary side, is it 1.25, Holly?
Yes.
It's a 1.25 multiplied by what current? By 3, not the 348, by the 278, the actual secondary current. So secondary fuse or circuit breaker, and that will get you, what's with these? That will get you 348 amps. And then you have to take the 348 amps, take it always to 240.6, and that will get you, and if it's not a standard, you go up or down. Does it have the note number 1? Yeah, if it wasn't a standard, make sure you guys put that little arrow here. Everybody's familiar with Chad's arrow here? Go up. So what's my next transformer up? 350 amp. 350 amp. 350 amp. So my secondary conductors are 350 amp.
Where did the 278 come from?
278 is the full load of the transformer.
Oh.
The full load of a transformer. Good point. It's the full load of a transformer. On the secondary side. On the secondary side. Okay, so we have a fuse. We have our fuse sized. Any question, guys? Before I want to size two more things, which is the bonding jumper for the separately derived system and the grounding electrode conductor. And surprise, surprise, guys, the bonding jumper and the electrode, the grounding conductor for the separately derived system is exactly like what we did for the services. You go to 250.66 for the grounding electrode conductor. For the bonding jumper, it's called not system, separately derived system bonding jumper. You go for that one, you go to 250.66. If it's higher than 1100 kcm, you take 12.5% of the feeder is feeding the transformer. The feeder is feeding the transformer. Any question? Bill, my friend, Jim, Camille, Brooks? No? All right, I'm going to go to number 5, if you guys don't mind. Number 5 is separately derived system, grounding electrode conductor for separately derived system. And I hate to get you hyped up on it. I just want, since we're doing transformers, might as well ground everything. 250, let's go to 250. Separately derived systems.
30.
Huh?
30.
250.30. 228.30. Grounding separately derived system. Grounded systems. System bonding jumper. Okay, here you go. And supply side bonding jumper. Grounded conductor. Grounding electrode. The grounding electrode shall be of the following. Grounding conductor separate shall be okay. It's actually for this one you will go to 250.30A5. So this is called grounding
In the 2000.
electrode conductor for separately derived why am I spelling is going out of whack here? Derived system. Okay, what did we say? 250? Is it different than 2008?
250, 30A,
Okay, 250,
30A3, and then
30 A
3.
3 in 2000. They changed them. I thought 5. The grounding electrode conductor single separately derived system.
3.
Is it 5? Wow.
250,
They shifted them.
grounding, electrode, conductor, separately derived system.
Okay, let's do it. Okay, 250.33. Thank you. 250.30A3. Right, Holly? Let's change them in 2008. Okay, if you guys go to that boy, and we'll tell you the following. What was the conductor feeding this? What was the conductor feeding this business? What is it? How many conductors? 500? Was it 500? Okay, let's take the 500 KCNM. Take this one to 250.30A3, and this will refer you to table 250.66. It refers you to 250.66. Okay, can you guys go there and size it? The 500 are the conductors on the secondary side of a transformer. The secondary side of the transformer conductors. The secondary side transformer conductors. Right? 500 kcm. The conductors on the secondary side. We size them, didn't we? Here, DJ. Where did we hear? These ones. The secondary feeders. We size, guys, the grounding electrode conductor for the separately derived system based on the secondary conductors of the transformer. Exactly like if it was a service. We do the same thing for service. Okay, what size did you guys come up with? 1 aught? I came up with 1 aught, one conductor, 1 aught. Anybody can tell me, does it have to be insulated? No, copper bare. Any question guys about this? Very, very important. So, and it's really not rocket science, it's just right on the stuff. All I want you to, number 6. The second one, guys, the main bonding jumper, they call it grounding separately derived system alternating system bonding jumper. And I have mine is 250.30A1, is it
Same, yeah.
the same? Okay. So
For your what? For your main bond?
system, it's called system, not main this time. System bonding jumper. Not main, system bonding jumper. The system, main bonding jumper is for the service bread. This is,
$250.
1 second, system bonding jumper. System bonding jumper 250.30
A1.
A and 1 as in 1. That's kind of smart, Alex. 250.30 A1. System. Now, I'm sure some of you are asking, Chad, what is the difference between the main bonding jumper and the system bonding jumper? Main bonding jumper is when you bring the feeders from the utility. Coming from the utility, you put them in a panel and you tie them to ground. That's main bonding jumper. You tie the neutral to the grounding electrode conductor in the service equipment panel. That's a main. The same. The calculation is the same, guys. If you have your own, this is my main, it's bonded. I moved in here. I had a new transformer to take the 480 into 280. Right to the guts of the transformer, I tie the neutral to the ground. So I established my own neutral. That's called system bonding jumper. Right to the transformer inside my building. This transformer I own, I operate, I maintain. That's my system bonding jumper. Okay, piece of cake. This is sized the same way, guys. If you go to 500 kcm, it's going to go to 250.30A1. It refers you to table 250.66. And if it was higher than that, it says somewhere. Yeah, it says somewhere where if it's higher than that, you have to go.
It refers you to 50.
Yeah. If it's higher than 1100 kcm, you have to go 12.5% of the feeder. So I'm going to write a note here. Well, let's take it 600 kcm. Is this higher? Let's see. Is this more than 1100 kcm? The answer here is no, right? Then the conductor will be the same. 1 aught. Let me repeat myself. Let me write it down. And let's just put it here. So the conductor should be 1 aught. That's my answer. Next to it, guys, if larger than 1100 kcm, then 12.5% times feeder conductors. Everybody can understand what I wrote here, guys? So 1 aught, but if the feeder was larger than 1100 kcm, then you have to take 12.5% times the feeder conductor size. Write yourself this note that will keep you energized for the rest of your life.
There's a step missing. in there.
Step? What's
It's 250.30A1 refers you to 250.28.
Yep, which goes, yep, absolutely. Yep.
Those of us not as smart as you. That's where you are.
That's where the little, okay, so it refers you guys, if you read through it, to table 250.28, article 250.28. But if you go to 250.30A1, you will find the answer though. And it refers you to 250.66, and let's write it down so we don't piss off my friend here. 250.28.
I've been pissed my whole life, Chad. It's all right.
Okay, now we're cool. So it refers you also to 250. That's a good point though. You're right, because a lot of, you're not familiar with it. So it goes to 250.28. Thank you. Now you guys go to work and you can bond and size a separated drive system. One more example about high voltage this time. The same thing, we're gonna do the same thing, another example, guys, for high voltage. Kind of tricky a little bit, for a high voltage. And then you guys are good to go eat. And then you start working on your one riser. And then what else we're gonna do? DJ, are you bringing your instruments tomorrow so we can dance and sing and all stuff? No? Seriously? You're not coming, are you? Oh shoot. Everybody's gonna be bringing some instruments so we can dance and do something productive in our life. Who's the musician? Ben? Ben can bring some instruments tomorrow? Extra credit.
I'll bring a boombox.
Serious? Bring some instruments. Electrical instruments. Okay, number 2. This is question number 2, guys. Question number 2. This guy is a high voltage, really. I'm going to have a transformer. It is my transformer. Almost always, guys, the primary of the transformer is a delta. Almost always. And the secondary of the transformer almost always is a Y. Delta Y. Okay? And for this boy, I need a fuse. I hope you understand, guys, with the fuse comes a disconnect, right? Because the fuses have to have a means of disconnecting them. Disconnect. I'm not worried about the disconnect, though. On the secondary side, I'm going to use a circuit breaker. And guess what I'm going to be doing? There we go. And I'm going to be sizing the following, exactly like we guys did. On the primary side, I'm going to be sizing number 1, the feeder. Number 2, the fuse. Number 3, the secondary fuse feeder. Number 4, the circuit breaker. And guess what? Since you guys are smarter than your teacher, we're gonna also bond. Here's a ground, and I'm gonna go bond. This is number 6, and I'm gonna go to Mother Earth, which I love dearly. Number 5. Okay, so we do the same thing as that we did, except the only difference is that this boy is the voltage on this boy. The voltage is, let's write it in a different color. The voltage here is 4160 volt. 4160. Even here they talk about 4160. And the kVA of this boy is 500 kV and A. And the voltage of this boy is 480 to 77 volt. And I'm pulling in neutral just to make sure that Mr. Ben is happy. A, B, C, and this is my A and my B and my C. Okay, so this is my transformer. Really beautifully done transformer. Beautifully drawn. That's debatable. It's moving. I thought for some second here. Okay, so we're gonna go, guys, size the feeders on the primary, secondary, the fuse on the secondary, primary, and the bonding jumper, and the grounding electrode conductor for. Is this a separately derived system, Camille? Separately derived system? Yes, it is a separately derived system. I'm creating a new neutral. Separately derived system. Okay. All right, let's go and start with number 1. Number 1, we need to size. Now this is a primary feeder, guys. Primary feeder. We're gonna go size primary feeder. Okay, I primary, Mr. Bab, equal. What do? The 500K divided by 1.73 times 4160. This is 4160 volts. Very commonly used voltage. in smaller communities, the top notch right now is 13.8. Okay, 4160. If you guys do the math on, I'm sorry, I just to stick with what can I ask you guys to do one little change. Actually, my transformer is, I forgot one. It's a 1500. Can you guys do me a favor? It's a 1500. The transformer is a 1500. Just add a 1 here, will you? 1500. Can you do me a favor, guys? Change 1500 instead of 500, 1500. Okay. Just to make it make sense on the medium voltage side, 1500. If you do that, you're gonna end up with 208 amps. 208 amps. 208 amps. 208 amps. Okay. Then you're going to take, again, this is debatable, but let's just continue doing it because a few smarter than Chad people are doing it. 1.25 continuous load multiplied by 208. Multiplied by 208. And gentlemen and lady, you come up with 260. 260 amp. Mr. Rebam, what do you do with the 260? 260 amp. You take it to which table? Let me see who's going to be making the mistake now. Wrong. Does 310-16 go up higher than 600 volt?
Oh, no.
That's catch 22. 310-16, guys, does not cover 4160. Look at the voltage. That's a high voltage cable. That's a high voltage cable. So I want you guys to move to a different table, which is the same way, but different table. And the table that I'm going to be using is 310.79. 310.79. 310.79. Can you guys go to this one? And under 90 degree column. Let's go to that boy. I have to go use the old code because my code different. This is a new table, guys. 310.70. Did I say 79? Yeah. 79. Okay. Everybody's there, guys? 310.79. 310.79. How about Chad if you go grab your code book and call it a day? 310.79. Close that one. Which table are we in here? They changed them. Why do they change things on me? 310. We're going to go to 310. And for these, 310, they put them on the end, didn't they? In the NEC code, no, not that one. Because I have it electronically. Okay, what am I chair? You give me 1 second to recode here. 310.
Gotta be close to 160.
DJ, I told you to hold your horses. Otherwise, you're gonna be. They named them. They named them. They changed the names for them. So it's basically still 68, 69. 310 the 60, 70. What did you say? 79. 310 the 73. Here you go, Chad. 310 the 75, 77. Good grief, 79. Here you go. I found it. In 2008 or 2009.
2009.
Okay, 310 the 17, 370. Keep looking at the 310. That's okay. Here you go. 310 the 70, almost there.
310.60.
Okay.
You
There you
know,
go.
you could just up in the fine there.
And you type it.
Yeah, and it
But
goes
that's
right
but
there.
that's kind of smart people do that.
Yeah, I know.
How are you going to be awkward if you do it? Okay, can you guys go to, you should be 310.79 use. This is the same table, this is just different name. This table is, I want you guys, 3 insulated copper conductor cable with an overall covering, blah, 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 in underground ducts. That's how you bring this table. Oops. This is 2011, the same table. You're bringing it underground. Here's what I'm going to bring to your attention, guys. Number one, what's the voltage level? What's the voltage level that we have? 4160. Because it's 4160, we're right in here. Had it been 13.8, Brad, where do you go? Right here. So then, what you're gonna ask me, Chad, type, what insulation do I want to use? The default, unless you know otherwise, is medium voltage. Right, 270. The default is medium voltage, unless you know otherwise. 90-degree column. That's weird because now they size a medium voltage based on 90 degree. We never do that on low voltage. On medium voltage, we size based on 90 degree. So 90 degree, here's my 90 degree, medium voltage cable 90 degree. And what was the amp? 260. So I need 260 under 90 degree. 260 is that 4 aught? That right here. Can you guys see that? 4 aught. Is that what I came up with here? What am I here? 4 aught. Okay, I want to bring your attention to, guys. So, so my current was 260. My current was 260 amp. When you take it to this table, which is a 310 dot, in my case 60C 2079, it will get you 4 aught. Next to the 4 aught, please write down what I'm going to write. Medium voltage dash 90. And how many conductors? 3. 3 conductors, 4 aught, medium voltage dash 90. MV medium voltage 90. The insulation are rated for 90. That's unlike everything that we did in low voltage. We never size conductors based on 90. We always size maximum 75. We derate based on 90, but we never size. Okay. Any question, guys, about this table? This is newly table that you're going to be introduced in the medium voltage cable. I want to bring your attention, guys, the smallest conductor you can use with this table is number 8. So if your calculation end up with anything less than number 8, what are you going to do, Brooks? Number 8, Jay. If you're using voltage 13.8, the smallest conductor you can use with it is what? Number 6. Okay? Any question, guys, about using this table? Jim, Camille, Bill, my friend, Mr. Rabab. Any question about using this table?
You say 3 aught for
It's a 4 aught.
oh, 310. Okay, yeah.
Why did you decide to go off that one when there's 3 different cables?
Very good point. Read to the top. You can choose anything based on, it becomes based on the installation. How are you going to be installing your systems? I have, if you guys look at, I'm going to bring your attention, I really don't want to go there. Here's, see where it says detail 1. Detail 1, the most common one is called detail 1. If you guys go back one couple of pages in your code book, you're going to find detail 1, 3 conductors and 1 dot. So these are basically 3 insulated cover conductor cabled within or overall covering 3 conductor cable in underground electrical dot. I have 3 cables in 1 dot. That's one way of doing it. You can have 3 cables in 3 dots. That's a whole different. The most common one, if you guys have the most common one for medium voltage, at this application as 1 big conduit underground with 3 cables coming in it. That's why I picked detail 1, not detail 2.
Where does it describe the detail?
The detail, go back to
On page 155.
yeah, page 155, and you can see how detail 2 is just 1 duct and multiple cables inside it. And I'm using, guys, a 3 conductor cable. A 3 conductor cable. 3 conductor cable, in this case, 3 conductor cable. There's so many applications. So there's so many applications, that's a good one. All right, I'm gonna go across this, bring it here, move to my next slide. Love technology when it works. Go back here. What was the size, guys, again? 3 conductors number? 3 conductors number 4 aught. 4 aught. Medium voltage 90. This is more important, almost. Okay, done. Let's go to, this is number 1. This is the hardest one, guys. The rest of them straightforward now. Can I move on? Okay, number 2. Oh, it's not here. This is also captured here too. That's nice. Number 2, what was number 2? Number 2 was primary overcurrent protection device. Okay, what was the full load current on that boy, guys? the fuse, the full load current was 208, multiply this one by 3. Where did I get the 3? This is from table 450.3A. Why A? Because it's one of them is higher than 600 volt. If you guys do this, you're going to end up with 624 amp. You're going to take this one to 240.6, and you're going to end up with beautiful. By the way, can you go up? Can you go up? Is there a note number 1? Yes. So if it's not a standard, Mr. Erbab, I have Chad's arrow here, and that will leave you with 700 amp fuse or circuit breaker. In this case, fuse, because we're using fuse here. Fuse. Is the multiplier, what's the multiplier for circuit breaker? 2.5? Circuit breaker on the medium voltage side. Or is it the same? 600. Okay, so we're using a fuse. That's why it's 3. Had it been a circuit breaker, that would be a big boy. Okay, piece of cake. You guys are smarter than my grandma. Number 3. Number 3. Any question about number 2, guys? Piece of cake, right? Camille, my friend. People are going to be, Camille and Chanel, we're going to pay you for doing that, guys. Okay, let's go to the secondary side. Secondary feeder. For the secondary feeder, guys, I secondary equal 1500 kc and m. No, what's kcm, Chad? Did I lose it? 1500 kVA divided by 1.73 times DJ. What voltage in the secondary side? 480?
480.
Yeah, 480. Thank you, DJ. So if you guys do the secondary, I came up with 1806. 1806 amps. This is 1806 amp. Did you guys come up with something different? Close enough? All right. Now we're going to size the conductors. You take 1.25. I hate to do that, but I do it. Times 806 equal. If you do that, you end up with 2258 amps. 2258 amps. Then, Mr. Rabab, you have 2 options. You can have a cover bus duct that carry this. You can buy a 3000 bus duct that can carry it in one bus duct, or you can cable it. We're going to cable it. So to cable it, I have 2258. I want to divide by 5 just because I'm the authoritative jurisdiction. You can divide by any number because I did it here. That will end up with a 500 amp. Am I right here? No? How much? 452. 452. 452 amps. Okay? And then if you take this one, take it to 310.16. Now, why 16? Because that's a low voltage side. What do you guys come up with? 900? What's 700? 700. 700. 700 kcm. How many conductors? I'm going to carry full neutral. 4 conductors. Assuming I'm going to carry full neutral, guys. Assuming I'm going to carry full neutral. Now, I want to bring to your attention, Brooks, that this calculation will change when I start putting a panel. If I want to put this in a panel, guys, I might have to go size based on overconduction device. I'm not putting it on a panel. Had I landed these cables in a panel to feed a panel, then my cables have to match the overconduction device in the panel. I'm not landing in a panel. I'm not assuming it's going to be landing on a panel. It could be a piece of equipment here that's fed from all this power. Okay, so that's basically what you, otherwise remember how you, after 800, you start matching the cable to the overconduction device? Any question guys before I size the fuse? So I have how many sets? I forgot to write the sets. 5 sets. 5. So this is my answer is 5 sets of 700 kcm. 5 sets of 700 kcm. Number 4. Number 4 is system bonding. No, we're going to do the grounding electrode. Grounding electrode conductor for.
Force overcurrent protection device.
Oh, thank you. Not even close. Secondary overcurrent protection device. Okay, for the secondary overcurrent protection device, guys, what do? We use the same thing, 11806 times it by 1.25. You end up with the same number, 2258 amps. You're going to take your 2258 amps and you're going to land this one on 240.6, and that will get you 2500 amp. 2500 amp. Now, Ryan, my friend, if this is landing on the panel and your panel is 2500 amp, you have to size the conductor based on the 2500 amp. I can't emphasize. Let me go back. Remember how we size these conductors? Assuming these are just feeding a machine, one machine. Okay? If you are to land these cables in 2500 switch gear, which is the most common application, 2500 switch gear, right? Then you have to size the conductor based on 2500, the overcurrent protection bus. Yes, sir. That's where it came up with the 900. And I'm going to do this one, guys. When I do the industrial, because we have panels, we start matching a transformer to a panel. And how are you going to do? So it's tweaking it to match a transformer to a panel. 250.
Yeah, I'm sorry.
Okay.
Why didn't you take that to 450.38?
To 450.3A.
1806 times, well, if we're using fuse or circuit breaker.
That's from 4. It is. The multiplier is from 450.3A. Not A,
Circuit
B.
breaker then?
I'm sorry. No, A. And what's the multiplier there? 125%. That's
Yeah,
where the,
all right, cool.
Yeah.
I didn't know if it was fuse or, I mean.
Yeah.
just don't-
Did we assume that's for 125 circuit breaker, right?
Okay.
Yeah. Is it different? They're different. What's the
They are
multiplier?
different.
What's the multiplier for the fuse?
2.5.
2.5. Yeah, we're using a circuit breaker. I thought that's what I did. No.
It's the
I
same.
am.
It's the same. Circuit
Oh,
breaker
that's
fuse
over
is the
600, yeah, you're right, sorry.
It's the same in that one. Okay. All right. So, in a case I'm not there, in a case like this one, guys, on the secondary side of that table, these two boys are the same. These two boys are the same. 50. There you go. Yep, absolutely. Yep, circuit breaker of fuse the same. Okay, so now we go to 5. Finally, Chad. We're going to go to 5. 5 is going to be the grounding electrode conductor for separately derived system. Separately derived system. I can't emphasize the word separately derived system. Okay, so how many runs did we guys run? We had 5 runs. 5 runs times each one of them is 700, right? 700 K. That will 5 times 7 is 3,500, right? 3,500 kcm. Then you take the 3,500 kcm. You take this one. Give me the, what was it, 250? 250.30 A1, I think, or
A3.
A3. And that will move you to table 250.66, and that will get you, no matter what you do, don't even dream of it. It's 3 aught. Now, one conductor, 3 aught. For the grounding electrode conductor, 3-aught. So no matter what you do, you're stuck with a 3-aught. The grounding electrode conductor. The system bonding jumpers will be separate, different. Okay, so that's my 3-aught. Number 6, my friends. Number 6 as system bonding jumper. System bonding jumper. You're going to do the same calculation, guys. You're going to take the 5, multiply it by the 700 kcm. It's going to give you 3500 kcm, and this is more than 1100 kcm. If it's more than 1100 kcm, what are you going to do, Brooks? 12.5%. I'm going to take it 12.5%. So this is 0.125 times what? 3500 K. 12.5%. My calculation was based on difference. So what's the answer for this? 12.5% times 3500. How much?
438.
438 kcm. And I don't know about you, Brad, but either you custom design yourself a cable this way, or where would you go? Anybody remember where we go? We go chapter 9, table number 8. If you guys go there, what's the next standard? 450? Do we have 450 or 500? 500, right? So how many conductors? One conductor. And what size? 500 kcm. And that would be my bonding, system bonding jumper that take my beautiful ground to my beautiful neutral and bond them together. Any question, guys, about ground? Give me the reference for it. I'm sorry. This is the reference for this one is 250.30
A1.
A1. System bonding jumper A1. That's where you do what you do here. 250.30 A1. 250.30 A1. Any question, guys, about the grounding electrode conductor for the separately derived system? System bonding jumper. Why didn't I write system bonding jumper for the separately derived system? Because system bonding jumper is always for the separately derived system. Grounding electrode conductor could be for the service or could be for the separately derived system. So this is SBJ 70 system bonding jumper is always for the separately derived system. And don't forget that here also we need to go to 250.66 table 250.66, and also so Brad will be happy, or is it 250.28? All these three guys will tell you to do what we've done. On the test, my friend, just write all these articles, bring them with you. No gimmicks, nothing. DJ, did I put you to sleep, my friend? This is really what you want to do about transformers. So we took 2 examples, guys. We did 3 things. First we talked about distribution system, different voltage and different transformers. Then we did 2 examples, one for a high voltage, and the other one for low voltage. One for high voltage, one for low voltage. So we can use the 2 tables, 450.3A and 450.3B. And I injected the grounding electrode conductor and the system bonding jumper because If you have a transformer, these two things you must be thinking about. How are you going to size the grounding, electrode, conductor, and the system bonding jumper? And everybody knows what they do, guys. They take the neutral bar, the cover bar inside the transformer, and they bus them together, either with a cover bus or with a cable. Just tie them together. And then they take a grounding conductor. In my case, it's 3/0, and they go all the way to the steel and CAD will directly to the steel through a connector. That's how you create a separately drive system. Mr. Rabab? Question?
No.
You can't stretch yourself. This is like an auction, man. You raise your hand, you buy. Any question, my friends? Brooks, my friend, anything I did wrong? No? Any? What's wrong, Greg?
Oh, I just saw Spencer roll his eyes back.
Uh-oh. Is it maybe it's time? Spencer, anything you want to go over? Makes sense? No? A little bit? The only thing I will bring to your attention, guys, really, is this table. This is very handy table for medium voltage. Mistake number one, a lot of people, oh, I know how to size cables. You go 310/16 because we've been using it. Yes, 90% of the time you're going to be in 310/16. But that 10% of the time, you might be in this table. Or any other tables. I brought you to one of them, guys. Using the rest of them, we're going to be using a few of them as we go. But really very easy. Read at the top and see. Sometimes you bring them in a cable tray. Sometimes you bring them underground. Single conductor cable. Sometimes multi-conductor cable. So it's unreal.
How do I know when you use this table instead of 310/16?
Very good point, Mr. Bab. When the voltage is higher than 600. When the voltage is higher than 600, I said this one time, and there was a guy in one of my classes, and he said, Chad, what would I do if my voltage, he has a machine that his voltage is 750. 750, very weird machine. If you guys look at 310/16, it says up to 2000 volts. So in reality, up to 2000 volts you can use. If you look at 310/16, it says 0 to 2000 volts. So any system 0 to 2000 volts is covered by 310/16. But 99.9% of the time, you're going to be basically anything higher than 600. Except as I said, when I said it one time, a guy said they have a machine in a paper mill, and that machine is running 750 special machine. How do you size a 750 kcm and 750 volt machine cable? 310/16. So when they say higher than 600 volt, it's not really right. 99% of the time isn't right, but so anything higher than 2000 really. That's a technical term, which is 99.9% anything higher than 600 volt. So if you guys so these are the tables they're going to be using. I want to bring you to your attention to the come on, Chad, since I have a few minutes here to bug you. Here's the details. If you guys look at the detail here, it says detail number one. Detail number one is a multi-conductor cable. That's what we used. Detail number one, this guy here is basically a multi-conductor cable. What is a multi-conductor cable, Chad? Is a conductor, here's 1, here's 2, here's 3, phase A, phase B, phase C, and if it's a medium voltage, you're going to find it's really weird because medium voltage, it's thick and insulation. Here's my multi-conductor cable. I decided single-handedly, Chad Curry, to use a medium voltage multi-conductor cable. You can use detail number 2, where you can put them in 3-dot single conductor cable. This guy here, you can use it as, here's my cable, one cable, basically one cable. Does it make sense? One cable and one dot. Where would I use this 1 versus 2? If your cable is huge, you can't fit it in one dot. Multi-conductor cable. Imagine these. What was the size? Our size was 4-aught. That's small. What if I need 500 kcm medium voltage? You can't. I don't think they make a 500 kcm multi-conductor cable medium voltage. That would be that big. So what do you need to do? They make a single conductor cable, 500 kcm, no problem. So then you use the detail, one cable per dot, one cable per dot, one cable per dot. And if you read through it, sometimes that detail is used also for multi-conductor cable, 3 parallel circuits. So for the most part, for you guys, you're going to be right, most likely right in this application here. But then if I can bury them, like this, direct buried cables or direct buried conductors. Then you go to a different table. So all these tables that you guys can see, 310-79 and 80 and 80, they are all based on different type of underground ducts, and almost all of them are underground, because when you bring the high voltage, you bring it underground. The safest way of bringing it. Look at this detail. This detail can bring you 6 circuits, multi-conductor cable circuits, 6 of them, or you can apply it for 2 circuits. Here's 1 circuit here, phase A, phase B, phase C, phase A, phase B, phase C, 2 circuits. Yes, sir.
Why would you use a multi-conductor cable in a single pipe? Like, let's say
Cheaper, easier
no,
than pulling 3 conductors.
well, multi-conductor is way more expensive than single. I'm just asking for like an example, because like,
Yeah.
if you're gonna pull like a 3-conductor 2-aught or something like that,
No.
it's a lot cheaper to pull 3.
These are medium voltage cable. The installation for a medium voltage cable is very expensive.
Yeah.
Very expensive. So if you can insulate them all in one, because what they do is they have a shield after a shield. I have one in my office. So if you have multi-conductor cable, you might be cheaper actually running 3 conductors. And I really didn't do the math, but that's one thing. The other thing is ease of installation. Installing 1 multi-conductor cable is much easier. Well, is easier, not much easier, than installing 3 cables, right? Because you're installing 3 cables. So that's one application.
The size, like,
That's why they allow you to go to different, if you can't fit them in duct, underground. And these are underground ducts. Underground ducts, guys, are not conduits. Underground ducts, I can make an underground duct, a 4-inch, well, not 4-inch, as a foot duct underground. 1 foot, I can't, and pull my cable in it. A foot diameter. These are not conduits. These are underground ducts. You can custom design any ducts to be, what's the size of these? They have a size somewhere on them. So they have the distance between them 7.5 inches. But what's the size of the ducts? Most of them are 5 and 6 inches ducts underground, but you can get it 8-inch duct diameter. So
I've actually
did you?
Yeah, it was for machines that go from the hallway into like a clean room build or area. So you ducts get up underneath the machine. That's all those multi-conductor cables.
You can
All the control is outside the room. So like if you have to change up relays or whatever, you don't have to go into the cleaner to do it. And they're like 3.
The single conductor cable, good application for if you have a 2000 kcm cable. I mean, you have anything higher than 1000 kcm, or probably, yeah, that would be a great application for single conductor cable, medium voltage. Because you just get too big, becomes a conductor. I don't know if you guys if anybody wants to Southwire, check Southwire. They have an MC cable, medium voltage MC cable, and see what the largest size multi-conductor that they make. Single conductor, they can go, I know that I have one in my office right now at 115, 2,500 kcm. 2,000, that's not even in any secret book. 2,500 kcm. So they make them custom design for any, and that would be feeding cities. I mean, 3 of these, the one I have in my office, 3 of them can guarantee you can cover 1/3 of the city of Minneapolis. Power, 1/3 of the city of Minneapolis. You can put them in 3 conductors I have in my office. They're running at 115,000 volt, 115,000 volt, and each one of them is 2,500 kcm. 3 of them for the 3-phase. You covered 1/3 of the city of Minneapolis. So it's a huge power you can get out of these. Any question, guys? My friends, this is all what I have for you. Tomorrow I'm going to do a couple of other things about transformers, and we're going to call it a quit until the holidays.